we've seen that the function of a lens is to converge a beam, specifically a convex lens, whether it is a light ray or with an electromagnetic lens, the electron beam is converged towards the principal axis of the lens. We've also seen that image is actually a kind of a two-dimensional distribution of intensity. We've seen some examples where from each pixel there is some value corresponding to an intensity. And when you put this kind of an object at the object plane on one side of the lens, we've also established that the Fourier transform happens on the other side, or at the other focal plane, you see the Fourier transform of the object. So what this actually establishes is a lens can be considered as a mathematical operator which is switching from the spatial domain to frequency domain, and the mathematical operation that is happening here is a Fourier transform. Let us understand this in a little more detail. What we'll do now is let us recollect how an image can be decomposed to various combinations of sines and cosines, or you can split all the information you have stored within an image to summation of various sinusoidal waves. And let us take an example of placing an object at the object plane of a lens and see how the Fourier transform of this looks like. And let us see what kind of simple changes can you make and how is it connected to the resolution. So we were looking at this example where this image on the left is formed by combination of three periodic patterns. So if I call the first one as psi naught sine k1 dot r, and the second one is psi naught sine k2 dot r, and the third one is psi naught sine k3 dot r, you can see that there are some subtle differences in the amplitude here. So let me write this as psi naught 1, psi naught 2 and psi naught 3, and I also have a variation in the frequency here. This frequency variation, as established, can be written as a dot product of two vectors, or I can take a sinusoidal waveform of the same period and change the angle of the propagation front. So if I write the propagation front here is in this direction, the second propagation front is here, and the third propagation front is here. If I take this as an object and place it in front of a lens, you would see not a direct decomposition in this way, but after I show you a practical example in the next slides, let us revisit this image and try to see how these wavefronts switch to the frequency domain and how the Fourier transform actually appears. Let me take a simple example. So I have an image of a flower here. This is a grayscale image, and if I take a Fourier transform of this, it appears somewhat streaky and random like this. Now I was just mentioning that each image can be decomposed into summation of multiple sines and cosines or multiple periodic functions, and it is not very obvious in a sample like this or in a material like this or in an image like this. So when there is periodicity, you will see that these intensity variations are a little more uniform. Nonetheless, you can see that there is some kind of a pattern that you can still notice here. There is some information here which is spread out, and there is some other information here. Now, each of these correspond to some features that are present here. So in fact, I will go back to the example of the sinusoidal waveform where we had only three sinusoidal wave patterns forming an image. This is a much more complicated one with numerous number of them, and if I take this as my origin and I write radial coordinates as frequencies, when we saw the derivation of the Fourier transform from an objective lens, if I call this as ki, you have several ki values starting from 0 to pi here. I am calling it as only 0 to pi because there is some kind of a periodicity on either side, and all the variations can be covered in this range of 0 to pi. If I start with 0 here, within this range, whatever variations in frequencies I have, starting from a point here to a point here to a point that I see here, this image can be viewed as something of this sort. This AIs are corresponding amplitude values of whatever I see here, and this KI corresponds to this particular vector. So I end up with an equivalent relation for the image I see here with something of this form. All these values which are corresponding to low values of K, I can call them as low frequencies. And all these higher values that I see here, which are slightly out of this particular range, I can call them as high frequencies. Now, the resolution of an image I record is proportional to the best possible highest frequencies I can record using the imaging medium. Or in other words, if I can think of the information I collect at the back focal plane, if I am restricting the information that passes through for further propagation and formation of an image, the higher ranges I can allow or the larger numerical aperture I have, the better resolution I get. Let us understand it with some simple examples of what is called as band pass filtering. We typically use these in image processing techniques. On the same object, let us apply a low frequency filter and see how the image looks like corresponding to the low frequencies. And also let us apply a high frequency filter just to get an idea that the information you see here, the streaks you see here, are not entirely meaningless and they are a one-to-one correspondence to the image. So if I look at the Fourier transform from the previous pattern, if I apply a mask like this and I am allowing only, so let us say I call this as K1, I am allowing all the frequencies within this radius of K1. Now this K1 can also be connected to the angle of scatter. So if I have this image in front of a lens here, or the object in front of a lens, at the back focal plane I can have an entire range of Ki, but now I am putting in a restriction or a kind of a virtual aperture here of a frequency value K1. And if I only use this information to construct an image, or in other words, if I take a inverse Fourier transform of this information, you can see that the image I see here is not as sharp as the previous information. And let me just go back. So if you see the details here at the outlines of this particular flower, they are not as sharp as you can see in this particular case. The outline is a bit more diffuse. This is all the high frequency values that I am cutting off. If I relate it to a simple photographic camera, the resolution of an image is only as good as the higher frequencies my camera can allow, or the resolution using this particular lens is only as good as the higher frequencies my imaging medium is allowing. Let me show the higher frequencies that we did not allow and how they comprise to form the other image. So if I just cut off the low frequencies now and only allow the high frequencies, you see the information I have here is like this. I see a bit more periodicity in this because there is some kind of an order here, but these high frequency values are corresponding to the sharp outlines that I saw. So this again reinforces the fact that if I have a lens which is allowing me larger frequencies to be collected, or larger angle of collection, or the larger angle of scatter that I have from the lens, I can get better resolution. Let me redo this again with the ray diagram. So if my object here is this particular flower, when this goes through my lens, and let us say I have the back focal plane here, all the parallel rays that go through will converge at the back focal plane, and I have some information here which forms. It is easy to think of a unidimensional Fourier transform when I represent it with some value x, but essentially the image I have here is in 2 dimensions, which is as shown here. If I define these as the frequencies in this direction as kx and this direction as ky, I can simply represent this image if I say I of x comma y. The information I have at the back focal plane is the Fourier transform of I of x comma y, but the intensity distribution in the Fourier transform is a function of kx comma ky. I can also write this as a Fourier transform of some unit vector r and the phase angle theta. I can always represent this with varying r and some theta or phi which corresponds to the phase. So the information I have in the spatial domain, I am transposing it into a frequency domain, and I have spatial distribution which I can give with Cartesian coordinates here on the left, and in the frequency domain I have a radial distribution. So when I display an image, this goes back to the information again stored in a matrix form. The image is simply a spatial distribution of intensity, whereas the Fourier transform, or I have also introduced this as the reciprocal space. In microscopy, this is very closely connected to diffraction. This is a angular distribution of intensity. Now, if I place a restricting aperture here, let me erase all that, and if I place a restricting aperture here, the radius of this particular aperture in the frequency space will give me the information on the resolution I have from the image. If I have a periodic pattern here, I would not see these continuous streaks here, but I would see distinct spots with varying intensities. And this is something we use in electron microscopy also to judge the resolution of your system. The farthest spots you get away from the center, the finest details you can resolve, and the higher the resolution of your microscope is. Okay, small break ikkada. Okay. So in other words, if the value ki here is corresponding to the angle alpha or theta here. Let me write it as simply theta. The resolution here of this particular lens corresponds to the frequency of k max, which in turn corresponds to this angle theta max. So, the larger your angle of acceptance or the larger your numerical aperture is, the better the resolution of your system is. So, for this reason, in optical microscopy, you have oil immersion lenses and so on, and in electron microscopy, when you are in particular doing imaging with STEM or even in TEM, the larger angle of acceptance you have for your objective lens, the better resolution you get in a microscopy system. Now, here we have seen a slightly more complex image, but let us look at more simpler images, or not really a crystalline material but a periodic pattern, and let us try to understand how the Fourier transform looks like at the back focal plane. So, I will go back to this composite image again, which comprises of 3 sinusoidal waves, and if I take a Fourier transform of this, as you can see from the center point here, I have 3 different K1, K2 and K3, and if I look at the real space variation of this particular sinusoidal wave corresponding to K1, it appears like this, K2 appears like this and K3 appears like this. There is again a one-to-one correspondence with the wave fronts I have here, and you see there is typically a 90-degree rotation when I take a Fourier transform. So, if I clear this and do this again, this wave front, let us say, is corresponding to the wave vector K3. If I rotate this by 90 degree, so from here I would get the K3 corresponding value here. This part is K3, and if I say this is K2, this would be K2, and this becomes my K1. So, here is K3, K2 and K1. So, all the intensity, all the summation of this psi naught 1, psi naught 2 and psi naught 3 is distributed now radially, and from a slightly more periodic image, you see the intensity is distributed only in form of some r comma phi here, where if I say phi is the phase angle here, this r can be called as the reciprocal lattice vector or your frequency space vector, and this is how a Fourier transform in a lens works like. And also, I think I might have given you the idea on how resolution is also connected to the maximum allowable frequencies here. This is about the function of a lens. Now, how does light propagate in general, or how does an electromagnetic wave propagate when there is no lens? You might actually see that there is a similar effect of light bending from a source when you are collecting information quite far off. This is something called as far field diffraction, and let us try to understand these concepts in the next slide. So if we try to understand propagation of light, if I have a point source, it is known that the flux emanating from the source goes radially in all directions. I have only drawn a section of this here, and in all the 360 degrees, so from, in principle, I would have the same flux emanating in all the directions. And if I go really far, let us say I place a slit here, far away from the light source, I would have more or less a planar incidence of light here. And let us say now this light source I am splitting into two sources, S1 and S2 here. Beyond the slit, the light again propagates like spherical wave fronts. And if I have a constructive interference between these 2 point sources, the light propagates forward in the forward direction, and I would have some kind of intensity distribution here. This is just a schematic representation of some kind of a principle we already know, called as the Young's double slit experiment. And the idea that light propagates in spherical wave fronts is from the Huygens principle. Let us say I have the so what the Huygens principle states is, I can consider that the light is propagating forward if and only if there is a constructive interference, and each point on this propagating wave front, I can consider it as an infinitesimally small source. That means from here to here, I have given you an example where I have a planar wave front incident on two slits here, but in principle, I can consider each one of these points here on the innermost propagating wave front that I have tried to draw here as an infinitesimally small source. So if light is propagating forward, if I take this as psi 1 and this is psi 2, and we know we can represent this as when the wave from these two sources, when the light from these two sources propagates forward, I can simply write them as summation of two complex wave vectors or two complex numbers, and if I say the resultant is like this is called as the position, the principle of superposition of waves. So I have given you an example of simply adding two wave equations here, which are psi 1 and psi 2, but in principle I have psi 1, psi 2, psi 3 and so on, psi n. From a point source, when light is propagating forward, I can simply take the resultant propagating wave front as sigma like this. And If I now simplify this and I only take two wavefronts here and the fringe pattern that I see here, that is what your Young's double slit experiment is. Let us say I have if I have a point source and light propagating through this, and let me call this as psi 1 and psi 2, and let us say there is a small angle here theta. You can see that for this wave and the second wave, the additional path difference that the second wave has travelled is, if I call it as some d, so this path difference chinna change ikkada. So let us say the path difference I have here is some delta, and if these slits are separated by a distance d, this path difference delta is d sine theta. So if I just take the simple trigonometric relation here, and if this path difference happens to be an integral multiple of the wavelength of the light that I have here, this is what we learned from the Young's double slit experiment, I have constructive interference. So if d sine theta is n lambda, the wave 1 and 2 successfully undergo constructive interference, and the path difference can be written as this. So going back to the previous slide where I have written psi 1 and psi 2 and the propagating wave as psi 1 plus psi 2, if I write psi naught sine let me write this theta 1 and the second one is psi naught sine theta 2, the propagating wave can be written as simply psi resultant is psi naught times 1 plus e power I phi, and this phi or the phase difference again is corresponding to the path difference I have here, which is d sine theta. So the resultant wave that is successfully propagated forward would have something of the form psi naught times 1 plus e power I d sine theta, and if I write the propagating wave vector has a wavefront k. This is the general form when two light sources are undergoing a constructive interference. In principle, based on this, I can have a summation of numerous light sources and get a resultant of the propagating intensity on the whole as a function of the path difference that I have here. So let us look at it. If we extend the Young's double slit to a really wide slit, let us say I have a case where I only have a large gap here, and let us say the slit width is 2a, and I am now collecting the intensity distribution really far away from here. Let me erase this. So you have a large slit of a width 2a. You can, in principle, do the following. So if I now have so let me recollect what we had here. If n lambda is b sine theta, and what I should be doing here is, instead of having summation from two individual slits, I have to integrate the complete intensity. So in the case of a double slit, so let us say psi resultant is psi naught 1 plus exponential kd sine theta. From here, if I want the amplitude, it would be bear in mind I can represent each of these with a complex number, and I can get the amplitude from the complex conjugate of this. So from this kind of a notation, I can end up with the intensity as a function of theta is in case of a double slit experiment. Now, we do not have a finite width here, but instead I can have an integrated intensity over the whole range starting from minus a to plus a. So if I write the integrated intensity when I have the field propagating, when I have the light wave propagating from a wide slit as the following. So if the phase shift is so when I have a large slit width, I theta is psi naught times integral minus a to plus a e power I kd sine theta times, let us say the slit width is some dx, if dx is the smallest slit. When I integrate this, this has a form psi naught e power I'll end up with something of this sort, and if I now normalize this and I write, say, kd sine theta with some value beta, this expression simplifies to I theta is some I naught times sine of beta a over 2 by beta a over 2 whole square. Or in other words, when I want to do the radial distribution of intensity as a function of a slit width, or let us say a slit width of 2a, I'll end up with a function which looks like this. Now if I plot this, this has the form like this. Now if I extend this to 3 dimensions, what I then need to do is I have to take a double integral over the entire circular aperture of e power I k, and let us say I now represent the variations for both the dimensions in the Fourier plane, for both the dimensions. Sorry, idokkati malli teeseddam Vijay. I mixed up something here. So if I move to a circular aperture, I was only looking at propagation of a unidimensional sinusoidal wave, but when I have an aperture now, I have an entire range and I can have two values of theta now which describe both the dimensions. So I have to do an area integral of to get the intensity distribution in the 2 dimensions. So if I have a circular aperture, the intensity distribution from a circular aperture takes a form like this, and from this, if I determine the intensity as a function of theta, I can simply say, let us say if the polar coordinates are x is r cos phi and y is r sin phi, provided the r value is lower than capital R, which is the radius of the aperture, I can write it as and if some alpha is kr sin theta, which is 2 pi r by lambda sin theta, the intensity distribution can be obtained from a function which appears like this, which is a function of 2 pi r sin theta over lambda over 2 pi r sin theta over lambda. cutting this short, I can simply get a value of intensity as some value I naught times so from a simple one-dimensional sine wave, where from a single integral you can get the intensity distribution as a function of theta, which appears like this. If I extend it to both the dimensions, it is essentially the complete plot of intensity distribution in 2 dimensions, which has a form like this. Essentially, these both are the same, but over here I have skipped past the complete derivation. It is only taking a double integral over the whole area. All you need to know is the intensity remains similar to that function, but instead of having a unidimensional variation like this appears like something called as an airy disk. Now, to summarize all of this, to understand light propagation or an electromagnetic wave propagation, we have seen from the simplest Young's double slit experiment, the intensity is proportional to the path difference or the phase here with this kind of a relation. When I have a wide slit, when I am integrating continuous sources over a width, I have the intensity is proportional to beta alpha over 2 by beta alpha over 2 whole square. And with a circular aperture, the function that I defined is called as the Bessel's function. It is proportional to the function over this, which has a sinusoidal form. And if I take the minima of this function to get the width of this particular plot here, you end up with a value where d is the diameter of the slit and I have lambda as the wavelength here. So, the radial distribution of the intensity here is proportional to something like 1.22 lambda over d. So, this is what you end up with. Now, linking this to the Raleigh's criteria and the resolution, if I have a simple point object, if I now use some kind of an aperture to image this, what we have learnt here from the previous couple of slides is, if light propagates from this point object in all the 3 dimensions and I am capturing with an aperture of radius r, this point object will be transposed to information which, when I take the histogram, appears like this, but when I look at the image in 2 dimensions, I see something like this. So, a point object is kind of spread like a function like this, and this relation is simply called as the point spread function from a circular aperture. We will always come across this in microscopy. So, essentially what this tells is, when you are using an imaging tool, a sharp point object appears to be spread over a slightly more distance, and this can be related with some kind of a mathematical relation where a Fourier transform of a point object, you end up with something which looks like this. Now, we know that this is a function of the wavelength and the slit width as well, or the radius of the aperture here as well. And how is this important, or why is this important, is if I have 2 closely spaced objects, if I use another color here, So, for two closely spaced objects, I'll have two point spread functions which are overlapping with each other, and if I can distinguish the gap between these two point spread functions from 2-point objects, I would have resolved them using my imaging tool. So, this is the concept of resolution. How do you see resolution of a lens? By looking at the reciprocal space or the backfocal plane. And how do you see 2-point objects which are spread like the point spread function here, and how do you distinguish them? So, if I apply that there are two minima here, or the two peaks of the airy discs here, and if I want to resolve them, I should be able to see them distinctly, and there are various definitions. Sometimes you see 50% overlap at the full width of half maxima is considered as resolution. Sometimes you see even if there is an overlap at 80%, or sometimes you would like to have a complete distinction, that is, I have two widely spread PSFs here from 2-point objects. So, we have seen this in very simplified terms as the Rayleigh's criteria, and we have written it as the resolution is something like 0.6 lambda by mu sine alpha, and this sine alpha mu becomes the refractive index, which is 1 here, and this becomes your numerical aperture of your lens. But essentially this is how all this came into place. So, a point object is not really remaining like a point object when it goes through an imaging system or a lens, and it spreads out, and you have the point spread function, and two overlapping point objects can be distinguished if and only if you can distinguish their point spread functions. And depending on the different conventions, you can either define it as even if 80% of the, if the 20% of the peak height is resolved, or there is an 80% distinction, or even 50% distinction in the peaks that you obtain, you would have resolved the objects. So, with this, I hope I have given you a flavor of propagation of waves. I have taken simply the parallels from light optics, basic wave optics, and tried to give you an idea of resolution and how the frequency space is related to resolution. Moving on from here, we will look at how an electron beam. So, in all these lectures now, we have seen, or in the last couple of lectures, so till now we have seen the propagation of light, where we have not considered the influence of a charged particle moving, and we have seen the interaction through either an optical lens or just a far field diffraction kind of a situation. But when you have an electromagnetic wave, an electron beam, which is a charged particle, interacting with a magnetic field of an electromagnetic lens, the situation becomes slightly more complicated. So, with this, I would like to conclude this particular discussion, and we will look at how the interaction of a charged particle or an electron wave with an isolated atom looks like, and then when you have a construction, or when you have the arrangement of atoms in a periodic fashion, how the phase of the electron beam changes. Thank you.